In Part 2 of Lecture 7, we will discuss memory partitioning. The principal operation of memory management is to bring processes into main memory for execution by the processor. In almost all modern multi-programming systems, this involves a sophisticated scheme known as virtual memory. Virtual memory is, in turn, based on the use of one or both of two basic techniques: segmentation and paging. Before we can look at these virtual memory techniques, we must prepare the ground by looking at the simpler techniques that do not involve virtual memory. The table in the slide summarizes all the techniques examined in this lecture and the next. One of these techniques, partitioning, has been used in several variations in some now obsolete operating systems. The other two, simple paging and simple segmentation, are not used by themselves. However, it will clarify the discussion of virtual memory if we look first at these two techniques in the absence of virtual memory considerations. In most schemes for memory management, we can assume that the operating system occupies some fixed portion of main memory, and that the rest of main memory is available for use by multiple processes. The simplest scheme for managing this available memory is to partition it into regions with fixed boundaries. Partition sizes are fixed in this instance, as you see in the slide, but they do not necessarily have to be the same size. Of course, one possibility is to make use of equal-size partitions. In this case, any process whose size is less than or equal to the partition size can be loaded into any available partition. If all the partitions are full, and no process is in the ready or running state, the operating system can swap a process out of any of the partitions and load in another process so that there is some work for the processor. There are two difficulties with the use of equal-sized fixed partitions. A program may be too big to fit into a partition. In this case, the programmer must design the program with the use of overlays so that only a portion of the program need be in main memory at any one time. When a module is needed that is not present, the user's program must load that module into the program's partition, overlaying whatever programs or data are there. Main memory utilization is extremely inefficient. Any program, no matter how small, occupies an entire partition. In our example, there may be a program whose length is less than 2 megabytes. Yet it occupies an 8 megabyte partition whenever it is swapped in. This phenomenon, in which there is wasted space internal to a partition due to the fact that the block of data loaded is smaller than the partition, is referred to as internal fragmentation. Let's talk about a placement algorithm. With equal-sized partitions, the placement of processes in memory is trivial. As long as there is any available partition, a process can be loaded into that partition. Because all partitions are of equal size, it does not matter which partition is used. If all partitions are occupied with processes that are not ready to run, then one of these processes must be swapped out to make room for a new process. Which one to swap out is a scheduling decision. This topic will be discussed later in the course. With unequal sized partitions, there are two possible ways to assign processes to partitions. The simplest way is to assign each process to the smallest partition within which it will fit. In this case, a scheduling queue is needed for each partition to hold swapped out processes destined for that partition. The advantage of this approach is that processes are always assigned in such a way as to minimize wasted memory within a partition, or, as we learned before, called internal fragmentation. Although this technique seems optimum from the point of view of an individual partition, it is not optimum from the point of view of the system as a whole. As we saw in a previous diagram, consider a case in which there are no processes with a size between 12 and 16 megabytes at a certain point in time. In that case, the 16 megabyte partition will remain unused, even though some smaller process could have been assigned to it. Thus, a preferable approach would be to employ a single queue for all processes, as we see in this slide. When it is time to load a process into main memory, the smallest available partition that will hold the process is selected. If all the partitions are occupied, then a swapping decision must be made. Preference might be given to swapping out of the smallest partition that will hold the incoming process. It is also possible to consider other factors, such as priority and a preference for swapping out blocked processes versus ready processes. The use of unequal size partitions provides a degree of flexibility to fixed partitioning. In addition, it can be said that fixed partitioning schemes are relatively simple and require minimal operating system software and processing overhead. However, there are disadvantages. The number of partitions specified at system generation time limits the number of active, that is not suspended, processes in the system. Because partition sizes are preset at system generation time, small jobs will not utilize partition space efficiently. In an environment where the main storage requirement of all jobs is known beforehand, this may be reasonable, but in most cases, it is an inefficient technique. To overcome some of the difficulties in fixed partitioning, an approach known as dynamic partitioning was developed. Again, this approach has been supplanted by more sophisticated memory management techniques. An important operating system that used this technique was IBM's mainframe system OS MVT, standing for multi-programming with a variable number of tasks. With dynamic partitioning, the partitions are of variable size and number. When a process is brought into main memory, it is allocated exactly as much memory as it requires and no more. An example using 64 megabytes of main memory is shown in the slide. Initially, main memory is empty except for the operating system, as you see in Figure A. The first three processes are loaded in, starting where the operating system ends and occupying just enough space for each process. We see these in figures B, C, and D. This leaves a hole at the end of memory that is too small for a fourth process. At some point, none of the processes in memory is ready. The operating system swaps out process 2 in figure E, which leaves sufficient room to load a new process, process 4, in figure F. Because process 4 is smaller than process 2, another small hole is created. Later, a point is reached at which none of the processes in main memory is ready, but process 2 in the ready suspended state is available. Because there is insufficient room in memory for process 2, the operating system swaps process 1 out in figure G and swaps process 2 in figure H. As this example shows, the process starts out well, but eventually it leads to a situation in which there are a lot of small holes in memory. As time goes on, memory becomes more and more fragmented, and memory utilization declines. This phenomenon is referred to as external fragmentation, indicating that the memory that is external to all partitions becomes increasingly fragmented. This is in contrast to internal fragmentation, referred to earlier. One technique for overcoming external fragmentation is compaction. From time to time, the operating system shifts the processes so that they are contiguous and so that all of the free memory is together in one block. For example, in figure H of the previous slide, compaction will result in a block of free memory of length 16 megabytes. This may well be sufficient to load in an additional process. The difficulty with compaction is that it is a time-consuming procedure and wasteful of processor time. Note that compaction implies the need for a dynamic relocation capability. That is, it must be possible to move a program from one region to another in main memory without invalidating the memory references in the program. Because memory compaction is time-consuming, the operating system designer must be clever in deciding how to assign processes to memory, or how to plug the holes. When it is time to load or swap a process into main memory, and if there is more than one free block of memory of sufficient size, then the operating system must decide which free block to allocate. Three placement algorithms might be considered are best fit, first fit, and next fit. All, of course, are limited to choosing among free blocks of main memory that are equal to or larger than the process to be brought in. Best fit chooses the block that is closest in size to the request. First fit begins to scan memory from the beginning and chooses the first available block that is large enough. Next fit begins to scan memory from the location of the last placement and chooses the next available block that is large enough. Figure A on this slide shows an example memory configuration after a number of placement and swapping out operations. The last block that was used was a 22 megabyte block from which a 14 megabyte partition was created. Figure B shows the difference between the best, first, and next fit placement algorithms in satisfying a 16 megabyte allocation request. Best fit will search the entire list of available blocks and make use of the 18 megabyte block, leaving a 2 megabyte fragment. First fit results in a 6 megabyte fragment, and next fit results in a 20 megabyte fragment. Which of these approaches is best will depend on the exact sequence of process swapping that occurs and the size of those processes. However, some general comments can be made. The first fit algorithm is not only the simplest, but usually the best and fastest as well. The next fit algorithm tends to produce slightly worse results than the first fit. The next fit algorithm will more frequently lead to an allocation from a free block at the end of memory. The result is that the largest block of free memory, which usually appears at the end of the memory space, is quickly broken into small fragments. Thus, compaction may be required more frequently with next fit. On the other hand, the first fit algorithm may litter the front end with small free partitions that need to be searched over on each subsequent best fit pass. The best fit algorithm, despite its name, is usually the worst performer. Because this algorithm looks for the smallest block that will satisfy the requirement, it guarantees that the fragment left behind is as small as possible, although each memory request always wastes the smallest amount of memory. The result is that main memory is quickly littered with blocks too small to satisfy memory allocation requests. Thus, memory compaction must be done more frequently than with the other algorithms.